Hi, and welcome to Lecture 9 of the Industrial Electricity K105 course. Today we're going to talk about a few things, and we will be referring to Chapter 7, Part 3 of the text. We're going to be doing a quick review of current divider. You've probably seen that a bunch of times now, but we're going to review it again. We're going to talk about a new subject called mesh circuits. We're also going to continue our introduction into AC circuits. The first thing I'd like to do, though, is to better answer a question I had from one of you about phasors. And if we look at a sine wave in the time domain, it would look something like this. And in the phase plane, it would be a phasor rotating around the axis. And if you think about this, and this is the real and imaginary plane, and so really the question is we've always shown this to be in a counterclockwise direction, and the question is it always in a counterclockwise direction? And the answer is no, it isn't. It depends on the waveform, and in this case, if you look at how this maps, we start at 0, it goes to 90 plus 90 as we go around the unit circle, as the phasor goes around the unit circle. And it goes to 0 again, and then to 270 degrees, and then back to the origin. So remember, the sine wave maps into the phasor diagram as a unit circle. And that's really, if you think about it, that's what an armature does, right? An armature is spinning in a circle, and that's why we get the sine wave from that, is because back in the time domain we actually get a sine wave. And if you actually looked at this with an oscilloscope, which we will be doing in a later lab, you'll actually see this sine wave over time. So really the question I had from one of you was, again, can it go in the opposite direction? The answer is yes. So if this wave were to start this way, okay, then the phasor diagram would be a phasor that rotates in this direction, because we would be starting at the origin, we'd be going to minus 270 and back to 0 again, so it would go this way. So the phasor would rotate this way. Okay. Okay, the first thing we want to talk about is we have a circuit here. We have a power supply, resistors, we have series and parallel resistors here. So what we want to do is find the current through R4, which is, I'm sorry, this is incorrect. It's really down here. Let's cross this out. We really want IR4, okay, which is down there. And so there's kind of two general approaches to this problem. We could determine a voltage across R4 using Ohm's law. We could also use the current here and use the current, and when I say here, I'm meaning right here, and we could then use the current divider rule. We could also measure the voltage across R3 as such. if we inserted 3 ammeters here, here, and here, the current through this path would be the same because it's in series. However, if we inserted an ammeter here and here at R3 and R4, they would be different. However, the sum of those two would equal any of the other ammeters in the series circuit. We could then calculate the current through the circuit by calculating the total resistance of the circuit and then use Ohm's law. So we could say R total, let me back up here, R total equals 10 plus 2 plus 5 ohms in parallel with the 10, and going back to that circuit just so you can see it. So we got 10 plus 2 plus 5 in parallel with 10. Becomes 10 plus 2 plus the parallel combination of this would be 3.3 ohms, which we could use our calculator to find that, and that equals to 15.3 ohms. So I sub S equals 100 volts over 15.3 equals 6.522 amps. We could then simplify the circuit and would look something like this. This becomes a current source of 6.52 amps. The resistor R3 and resistor R4 equal to 10 ohms, and this is 5 ohms. Okay. We can use the current divider rule now and say that I sub x, the current of interest, equals RT over Rx times IS. The parallel piece is 3.3 ohms as calculated before, so then IR4 equal to 3.3 over 10 times 6.52, and that equals 2.17 amps. This RT is not the total resistance of the whole circuit, it's of the parallel piece, and that's a mistake that many make. Okay, next topic. Let's talk about mesh circuits. So a mesh circuit is neither a parallel or series circuit. Let's see, slide 3, there we go. Okay, so we'll take this example circuit here, and we see we have a 5 volt voltage source, we have a 2 volt source and another 2-volt source over here with some resistors. We have current through 2 loops. We have IA sub A and I sub B. Currents should always be, by the way, drawn in the clockwise direction for convention. So that's something to keep in mind. And we have an observer here looking up, and he will go around the loop as we've done before. So if we write an equation for the first loop here, we can say that minus 5 as we go in here plus VR1 plus VR2 is equal to 0. And that's using our KVL law, again, where we say the sum of the voltages around the loop are equal to 0. And we could write a second equation for loop B. We could say VR2 minus 2 as we go in this direction. Okay. Plus VR3 plus 7 equal to 0. Now we want to make substitutions for all of the voltages using our little formula here. E equals I over R. So the first equation becomes minus 5 plus 2 I sub A plus 4 I sub A minus 4 I sub B equals 0. So we need to subtract the voltage here due to the fact that IB and IA are in different directions. So we have a current in both directions affecting the voltage across the 4 ohm resistor. So this becomes 6, if we add the IAs up together, we have 6 IA minus 4 IB equal to 5, so that's equation 1. And then equation 2 is 4 IB minus 4 IA minus 2 plus 4 IB plus 7 equals 0. And that becomes a minus 4 IA plus 8 IB equals to 7. So we can solve these two equations as it has, there's 2 equations and 2 unknowns. So we can put these equations into a matrix form and solve them with a calculator. And so it would look like this: 6 minus 4, 5 minus 4, 8, and minus 7. Remember, these are the coefficients of the variables on the left side of the equation, and these are the numbers on the right side of the equation. So this is how you set this up for a matrix. We can use our calculator to calculate this. We need to go into a different mode here. We need to go mode, hit the mode button, and then mode 5, and then we're going to select 1, and we can enter our coefficients now. So we can say 6 equals, and you can see it went into the top left matrix, column of the matrix, and then we have a -4 equals, and a 5 equals, and a -4 equals, and an 8 equals, and then a -7 equals. So our I sub A would equal to 0.375 amps, which equals to 375 milliamps. I sub B equals, hit the equals one more time, and we'll convert that to decimal. So that's equal to a minus 0.688 amps, and that's 688 milliamps. Now we can find the voltage across R2. So we have 375 going this way. We have minus 688. However, because we've defined the current in this direction, it becomes a plus 688 in this direction, down through the resistor. So this becomes is 4 ohms, 1.06 amps, which then voltage across R2 equal to 1.06 times 4 equals 4.2 volts. So let's look at another example. So here's the circuit of interest. We'll now write equations for that. So the first equation will be 4IA minus 10 plus 6IA minus 5 plus 2IA minus 2IB equals 0. Let's go back to that circuit. Okay. Again, we need to subtract the currents here because we have current flowing in one direction. IB is flowing up through R3, and IA is flowing down through R3. And then our second equation would be, get our other color here, 2IB minus 2IA plus 5 plus 3B plus 3 equals 0. And now equation 1 becomes 12IA as we group elements here together, minus 2IB equal to 15. And then equation 2 becomes minus 2IA plus 5IB equal to minus 8. Negative 8. Whoop. There we go. And we'll put this again in matrix form like we did before. So we have a 12 from this coefficient. It goes here. And we have a minus 2 going here. And a 15 from here. And a minus 2. And a 5. And a minus 8. And again in our calculator. So we'll put in 12 minus 2, 15. Minus 2, 5, and finally minus 8. So we get I sub A then equal to 105 amps, and I sub B, hit that equal sign again, a minus 1.18 amp. So again, some advice here, as we mentioned before, always show the currents going in a clockwise direction, and also start at the lower left-hand side of the circuit as you traverse around each loop, here and here. It'll be very helpful in calculating these circuits. We're going to continue our discussion with our intro to AC. Last time we talked about VRMS is equal to V peak over square root of 2. And if we do V of T equal to 650 cosine of 377 T minus 120 degrees. This is our V peak. This is omega equal to 2 pi f. So omega equals 377. And this is our phase shift. Which is negative in this case. So we can rewrite omega here as omega equals 377 equals to 2 pi f, which implies that f is equal to 60 hertz. So 1 over f is the period, is equal to 16.7 milliseconds. So now we can sketch this waveform. We have voltage. Time. if we were to sketch a cosine wave, it would look something like this. Here's 90 degrees, 180, 270. So it would look like something like this. But in this case, we have a phase shift of 120 degrees. So then the wave would actually look like this. So this is delayed by 120 degrees. And our peak amplitude would be 650 and minus 650. If we looked at this in a phasor diagram, this would look like this, real and imaginary axis. It would be a phasor that was over here, 460 volts RMS, and it would be delayed by 120, minus 120. So let's talk about three-phase. So this is what it would look like. This would be phase A. This would be phase B. And this would be phase C. So each one of these is delayed by 120 degrees from each other. If we looked at this in a phasor diagram, it would look like this. This would be 460 volts RMS. This would be phase B here. And this would be 460 volts RMS. An angle of minus 120. And then finally, phase C would be up in here. This would be 460 volts RMS with another 120 degree of delay. So now let's talk about a three-phase system that you would see in industry, on your poles, and the world really lives with a three-phase system. So we have three phases: phase A, phase B, and phase C. And then we have a neutral wire, and then a ground wire. So in a three-phase system, we would take a motor like so, and we would hook up phase A to it, phase B, and phase C. And we'd also put a safety ground on here as well. That would be very important to do that. But no neutral. we also can derive 120 volts from this. So and it can be done from any phase to the neutral. So if we and this is how our house is hooked up. We take this, we run it in this a plug that would go to the neutral wire. And then also we have a ground wire here that would go to ground. So this is 120 volts AC. This system is a 208 volt AC system. So we can get 208 for motors, to operate a motor or a three-phase device, and we also can get 120 volts AC for our house. So the question you might ask is, how do we get 120 volts from 208? So here's how. If we configure 3 resistors in this configuration, and this is called a Y configuration. It's an upside down Y, but you can see the Y here. So we have 3 phases coming into each resistor and a central point and we tie that to neutral. So if we put a voltmeter in here, we would measure 120 volts AC. If we go across 2 phases, instead of 1, go across 2 resistors, we'll see 208 volts AC. Another configuration of a 3-phase is called a delta. And it looks like this. 3 resistors. Phase A, Phase B, and Phase C. Notice that the delta has no neutral or center point. So the question is, why 3-phase? Well, in a single-phase system, let's start with a 10 horsepower motor. Same thing with a 3-phase system, and that would cost about $2,600 to run for a year. The 3-phase would cost $2,100. The single phase is 82% efficient, whereas the 3-phase is 90% efficient. A single 10 horsepower motor, a single phase 10 horsepower motor would weigh about 170 pounds, whereas a 3-phase would be 120 pounds. 3-phase systems are more efficient, cheaper to operate, obviously, and some common voltages are 208, 480, and 4160. The equation for 3-phase would be VPP, which is the line-to-line voltage, equals the square root of 3 times VPN, and this is the line to neutral, and EU, neutral. Okay. In the previous example, we would have 208 equal to the square root of 3 times 120. Remember this equation, put it on your note card. You'll be using that for quizzes and tests. So let's go back now and talk about capacitors and inductors. So we have a capacitor, has two plates with a dielectric or an insulator between the two plates. We have an inductor, which is a iron core, and has what we call magnetic storage. The capacitor has electrostatic storage, and the inductor has magnetic storage. We can write an equation for the energy on a capacitor as is 1/2 CV squared, where C is the capacitance. And we can write an equation for the energy on an inductor as 1/2 L I squared, where L is the inductance. We can write an equation for the capacitor reactance. X sub C is 1 over 2 pi Fc, as we discussed in our last session. And the inductive reactance, X sub L, equals 2 pi Fl. We can write an equation for the impedance of the capacitor, which is a vector, as we said. And A equals minus JXC, and the impedance of an inductor equals XL. In the real and imaginary axis, we see that a resistor lies along the real axis. A capacitor is down here, so the capacitor reactance is an angle of minus 90 degrees. An inductor lives up here, where the inductive reactance, I should say, is plus 90 degrees. Eli the Iceman, remember this? We have an inductor. We have the voltage, VRMS. Voltage leads the current, IRMS. So voltage leads current. For an inductor. We have a capacitor. We have the voltage RMS. And the current. And we see that current leads voltage. Now I'd like to talk about power in AC circuits. So inductive and capacitive circuits have reactive power. And that's power that does no work. it goes back and forth between the generator and the load. And that's because it's in the imaginary axis. The metric for the power factor is the cosine of theta, where theta is the difference in degrees between voltage and current waveforms. Now I'd like to do a look ahead to what we'll be looking at shortly. As you know, we have AC, DC, we have the E over IR. In AC, it's V vector voltage, which is current times the impedance. And the power in a DC circuit is IE. And in AC circuit, it becomes S. This is the power vector over I star. This is the voltage vector. And this is the complex current. We'll talk about that later. We can also talk about power triangles, and we saw this last time for an inductive circuit. And for capacitive circuit. The circuit looks like this. This is the apparent power. This is the real power. This is theta, and this is the reactive power. In a capacitive circuit, looks like this. This is the real power. This is the apparent power. This is reactive with angle theta. You actually measured these in the last lab. You had a circuit like this. You remember this circuit? You had a voltage input, 120 volts. You had an ammeter, voltmeter, wattmeter, and you had a resistive load. And your wattmeter connected to the DC power supply. And then you outputted 25 volts at 1 amp. If you remember, we had a maximum output of 1 amp on the power supply. And so from this we drew triangles. And on the wattmeter we were looking at 120 volts. We measured that. We had current we had VA, volt amps, we had peak to peak, and we had frequency. So the reason why we had a difference in our, or we had reactive power, is because the power supply actually had a inductive component. So that's going to do it for today, and we will see you next time.